Have you ever really stopped to think about what makes your phone light up or what keeps a whole city humming with power? It all, and I mean all of it, comes down to electric circuits. They are the invisible highways that run our entire modern world. So in this explainer, we're going to open up the toolkit and really build a solid understanding of how these circuits actually work. Let's dive in. Now, what you're looking at here, this isn't some sci-fi movie set. This is a real, massive battery storage plant. For a time, it was the world's largest, and it's capable of powering tens of thousands of homes. And what's so amazing is that the simple, fundamental rules we're about to cover don't just work for the tiny gadget in your pocket. These exact same principles scale all the way up to managing the power grid for an entire country. Okay, so for charges to flow, to get a current, you need a push, right? You need some kind of steady pressure to keep things moving. But what provides that constant push? Well, that brings us to the first and most important piece of our toolkit, the engine of the circuit. And that engine is something we call an EMF device. Now, EMF stands for electromotive force. But honestly, that's a terrible name because it's not a force at all. It's much, much more helpful to think of it as a charge pump. Its only job is to do work on charges, to basically lift them from a low energy level to a high energy level, giving them the potential they need to make a trip around the circuit.
Here we go. This is about as simple as a circuit gets. The battery, that's our EMF device. And you see that little arrow inside of it? That arrow represents the EMF, and it always points from the negative terminal to the positive terminal. That's the direction the pump is pumping. That charge then flows out the high-energy positive side, travels through the resistor where it does some work and loses its energy, and then comes back to the negative side to get pumped up all over again.
You know, this formula right here, it's not just some random math. It tells a really powerful story. It's the very definition of EMF. That fancy epsilon symbol, the EMF, is just the amount of work, dW, that the pump does on every single little unit of charge, dQ, that passes through it. So you can think of it as the specific energy boost that each and every charge gets for its journey. Now, in a perfect physics textbook world, we'd have ideal batteries with no issues. But here in the real world, every single EMF device has some internal resistance. Just think of it like a little bit of friction inside the battery itself. And because of that friction, when current I is flowing, that internal resistance R eats up a tiny bit of voltage. This means the actual voltage you can use at the terminals, V, is always just a little bit less than what's printed on the side of the battery. All right, we've got our engine. Now we need the rules of the road. And here's the beautiful part. No matter how complicated or frankly nuts a circuit looks, it will always obey two beautifully simple laws figured out by Gustav Kirchhoff. These are our absolute essential tools for figuring any circuit out. First up is the loop rule, and this is really just a fancy way of talking about the conservation of energy. The best way to think about it is to imagine you're hiking a mountain. You go up some hills, you go down some valleys, but when you walk in a complete circle and end up right back where you started, what's your net change in elevation? It's zero, right? A circuit loop is exactly the same. All the voltage gains from the battery and all the voltage drops across the resistors have to perfectly cancel each other out. And check this out. This graph basically proves that mountain analogy we just talked about. If we start at point A, our potential, our elevation, is zero. As we move across the battery, boom, our potential jumps way up. Then, as the current flows through that little bit of internal resistance and then the main resistor, the potential drops and drops until it comes right back to zero where we started. The loop is complete and everything balances out. So how do you actually use this rule? It's super simple. It just boils down to two things. First, the resistance rule. If you trace your path through a resistor with the flow of current, the potential drops. It's like walking downhill. If you go against the current, the potential rises. And for a battery, it's even easier. If you move in the same direction as that EMF arrow, from negative to positive, the potential rises. You're going up the ski lift. The second rule is the junction rule. And if the loop rule was about energy, this one is all about conserving charge. Imagine a bunch of water pipes meeting at an intersection. The amount of water flowing in has to equal the amount of water flowing out, right? Water can't just vanish or appear out of nowhere. Well, charge works the exact same way. At any point where wires meet in a circuit, the total current coming in has to equal the total current going out. So let's just put them side by side to make it crystal clear. The loop rule is about energy conservation, and it lets you track voltage around any closed path. The junction rule is about charge conservation, and it lets you track current at any intersection. That's it. With just these two rules, you have everything you need to solve pretty much any DC circuit you'll ever see. Now, let's be honest, circuits can get messy. You can have resistors all over the place, making it really hard to see what's going on. So our next tool is all about tidying up. Turns out, we can often simplify these complex spiderwebs of resistors by replacing a whole chunk of them with one single, simple, equivalent resistor. Okay, so there are really only two basic ways you can connect resistors: in series or in parallel. And the difference all comes down to the path the current takes. In a series circuit, on the left, the current is on a one-lane road. It has no choice but to flow through every single resistor, one after another. But in a parallel circuit, on the right, the current gets to a fork in the road and it splits up, with some of it going down each path. When resistors are in series, calculating the total resistance is about as easy as it gets. You just add them up. Simple as that. The most important thing to burn into your brain for series circuits is this: the current is exactly the same through every single one of those resistors. Parallel circuits are a little different. The math looks a bit funkier. You add up the reciprocals, but this leads to a really interesting, kind of counterintuitive result. The total equivalent resistance is always less than even your smallest individual resistor. Why? Well, because you're opening up more lanes for the current to flow, making it easier overall. And the key takeaway for parallel? The voltage is the same across every single branch. All right, so this table right here, this is your cheat sheet. Seriously, nail this down and you're golden. For series, current is the same, voltage splits up. For parallel, voltage is the same, current splits up. Understanding this one fundamental difference is the absolute key to simplifying circuits the right way. Up until now, everything we've talked about has been steady, constant, kind of boring really. The current just flows. But what happens if we throw a component into the mix that actually cares about time? Let's add a capacitor and see how the whole personality of the circuit changes. This is your classic RC circuit. You've got your battery, your resistor, and now this new player, the capacitor, all hooked up to a switch. So the question is, what happens the moment we close that switch and let the battery start trying to charge up that capacitor? This one graph tells the entire story, and it's awesome. The instant you close the switch, the capacitor is empty, so it's like a wide open door. Current rushes in at its absolute maximum. But as charge starts to build up on the capacitor's plates, it creates this sort of back pressure that makes it harder and harder for more current to flow. So the current dies down exponentially towards zero. Meanwhile, the charge stored on the capacitor grows exponentially until it's full. They're perfect mirror images of each other. So how fast does all this happen? Is it instant? No. The speed is set by something called the circuit's time constant, represented by the Greek letter tau. And it's incredibly simple to calculate. You just multiply the resistance by the capacitance. This single number, tau, defines the whole timescale of the circuit. In fact, after exactly one time constant has passed, the capacitor will have charged up to about 63% of its total capacity. And what goes up must come down, right? Discharging the capacitor is basically the same movie, just played in reverse. If we take the battery out and complete the circuit, all that charge we stored up, Q0, will start flowing back out through the resistor. As you can see from the formula, the charge just drains away exponentially. And what governs how fast it drains? You guessed it, the exact same time constant, tau. Okay, so why in the world should you care about any of this outside of a physics lab? Well, let's talk about a race car. As this car is flying around the track, friction from the air and the road builds up a huge amount of static charge. The car's metal body and the pavement below basically become the two plates of a giant capacitor, and it's storing a ton of energy. And when that car pulls into the pit, all that energy has to go somewhere. And this brings us to the final and most critical question. If all that stored energy is released in a single spark right next to highly flammable racing fuel, you get a catastrophe. The car and its tires actually form a real-life RC circuit. By understanding the time constant of that circuit, engineers can design tires with just the right amount of resistance to let that dangerous charge bleed away to the ground safely and super quickly, in just fractions of a second, long before a deadly spark can ever form. It is a life-or-death application of the very physics we've just been exploring.